So our next speaker is Brian Macdonald. So Professor Macdonald has a Ph.D. in mathematics from Johns Hopkins University. He is special faculty in sports analytics in the Department of Statistics and Data Science at Carnegie Mellon University. Previously, he was the director of sports analytics in the Stats and Info group at ESPN. And he was also the director of hockey analytics for the Florida Panthers Hockey Club. So welcome, Brian Macdonald.
So first of all, thanks to the organizers for inviting me to speak here. So I'm going to talk about some of the work that I did at ESPN, starting with Real Plusminus, and mostly sticking with NBA related things, but we'll talk about all sports analytics in the COVID era a little bit also. And so let's start with Real Plusminus, and basically here's the sort of the goal, the high level goal of this Real Plusminus metric. So actually, first I'll back up for a second and just talk about why does ESPN have a sports analytics team. So ESPN, I think the sports analytics team was founded about 10 years ago, roughly in that area, and one of the main reasons it was created was because teams were using analytics and data to make decisions. And if ESPN was going to be able to talk intelligently about those decisions, one of the ways that they have to talk about those decisions is from an analytics perspective, because teams were using analytics as part of the decision-making process. So they created a sports analytics team, and that team works on creating metrics that are similar to the ones that the teams use internally, and also works on other metrics that maybe the teams wouldn't necessarily be interested in, but are useful for the purposes of storytelling in sports. And so Real Plusminus is one of the metrics that's good for both. Like a team would find this useful, and it's also good for storytelling. So Real Plusminus, so the purpose of this is to create a statistic for NBA players that estimates each player's contribution to his team, accounts for his teammates and opponents, because who you play with can affect, for example, how many points you get or how many assists you get and things like that. We want this statistic to stabilize fairly quickly in the beginning of the season and only use information from a single season. So you could definitely get a better metric for player performance by using multiple seasons of data. But one of the reasons that one of the use cases for this metric is to be able to talk about, MVP race, all-star selections and things like that. So things that have to do with only this season. We'll talk about a multi-year version of Real Plusminus a little bit later, but that's the goal. For now, that's the goal of Real Plusminus. And so just a little bit of history about these kinds of metrics. This is not like the first of this type of metric. And there were building blocks that came sort of before Real Plusminus. So, so this was originally created by Jeremiah Engelman, and with help from Steve Olardi. And there were some sort of building blocks even before that. So early models that were called adjusted plus-minus models, they used these on-court, off-court data. So they used substitution information, so you know who's on the court at any given moment of the game. And then for each time period during a game when there was no substitutions, they would use points that the home team scored and points that the away team scored. And from this, you can imagine getting, for each player, how many points the team scores when he's on the court versus how many points the other team scores when he's on the court. And that's actually plus minus. You get a +1 for every point your team scores. You get a -1 for every point the other team scores. And what these adjusted plus-minus models did was use regression techniques to account for the other players on the court when this happens. And So it's kind of like a plus minus that's adjusted for how good the teammates and opponents are. And another kind of model was a box score plus minus model, which was basically a model that was a weighted average of box score statistics. So weighted average of things like points, rebounds, assists, and other box score statistics. And so what Real Plusminus did was sort of combine the best of both worlds here. So they used, the original model used this on-court, off-court data that I mentioned with substitution information, and then what the team did when these players were on the court. And it also used individual box score statistics. So it used both of these things at the same time. And for those familiar with ridge regression, the original Real Plusminus was sort of a modified ridge regression, which is different because instead of shrinking all of the player ratings or the player coefficients towards 0, it shrunk them towards this box score plus minus that I talked about. And then it also shrinks different amounts for offense and defense. So this was the original idea of Real Plusminus. It's a metric that estimates a player's overall contribution to his team, and it uses the box score statistics, but it also uses what does the team do when you're on the court versus when you're off the court. And that's important because box score statistics don't measure everything. If you're really good at boxing out someone, boxing opponents out for a rebound, but someone else on your team gets the rebound a lot, you don't necessarily yourself get that rebound. You're obviously contributing to the team's success, but you're not getting any individual box score statistics in that particular case. So it's useful to use both of these kinds of data in a model to measure a player's performance. So unfortunately for the public, I guess, Jeremias joined the Mavericks. And so he wasn't going to be able to do this publicly anymore or for ESPN anymore. And so the ESPN analytics team recreated this internally. And we also added some new features. So some of these, like Jeremias didn't have access to. So internally, we had some advanced box score statistics from Second Spectrum data, which is a third-party data provider. They're kind of like StatCast, but for the NBA, essentially. So advanced box score stats that come from player tracking data. And so in the NBA, there's cameras in the ceiling tracking the location of players and ball throughout the game. And from that, these advanced box score stats are extracted from that location data. And so we have those from 13-14 season to present. And so we used some of those in the model. We'll get into a little bit more details in the next slide. There's also matchup data that comes from you can imagine an algorithm determining who is matched up against who on every possession. And so we derive some things using that data. We kind of use a very similar model, but with a key difference. We use the Bayesian regression model, which basically, instead of getting just a number for each player, we're getting a full range of possible values for their Real Plusminus, and then how likely each of those are to occur. So we're getting like a full distribution instead of just a single value. And then we went back a little bit further in time to the 96-97 season. We have to keep in mind that this data did not exist back then. So we have sort of a different model for before 13-14 and after, and 13-14 and after. So just a little bit more details about some of these things. So here are some of the advanced box stats that we used in the model that turned out to be important. So one of them is passes ahead in transition. So this is like, passes in fast breaks and things like that. And this turns out to be pretty important for offense. Someone like LeBron James is usually high in this because he does this a lot. But yeah, passes ahead in transition, which tend to lead to either dunks or easier buckets than something shots that are generated in a typical like half-court offense. Time of possession was an important factor. It was actually it affects a player's rating negatively. Essentially, it's because if all other stats are equal and that player's time of possession is higher, that means he was slightly less productive given how much he had the ball. This third one is shots within 18 to 24 seconds of the shot clock. That is essentially, that's important because of this. These are mostly like transition buckets. And then deferred defensive rebounds. This is kind of like what I talked about before. If you box someone out and you don't get, and your teammate gets the rebound, that's like a deferred defensive rebound. So I mentioned the matchup data. And so with the matchup data, you kind of have, for every possession, you have who is guarding who, and then what happened what happened during that possession. And so this allows you to create some matchup adjusted box stats, which is what we were calling them. So for example, for field goal percentage is a standard box score statistic, but that can be impacted if you're the best player on your team, the best offensive player on your team, you're probably matched up against one of the best defenders on the other team most of the time. And so that can tend to have an effect on your field goal percentage. Maybe it would be lower than if you were typically matched up against an average defender. And so that's what this adjusted field goal percentage attempts to do. So it estimates what would this offensive player do if he were matched up against an average defender? What would his field goal percentage be if he were matched up against an average defender? And then we can do the other thing. We can flip that, do the other thing from the defensive perspective. So opponent's field goal percentage, first of all, wasn't ever really a standard box score statistic. You couldn't find this in a regular box score before player tracking data. So this just even the unadjusted version of this is a help. And maybe teams this is probably being tracked privately by teams and maybe other third-party data providers, but it wasn't really widely available until recently. So that's opponent field goal percentage. Like for the shooters that you're matched up against, what is their field goal percentage if you're a defender? And then the adjusted part is, you're adjusting for the quality of the shooters that you're matched up against. So this would be like this is an estimate of what would we expect this defender, what would we expect his opponent's field goal percentage to be if he typically faced average opponents. And then we have stats that are similar to these, but for 3-pointers and for opponents' 3-pointers. And this just gives an idea of like what are the what range of values do these new statistics have, essentially. So this is field goal percentage. The left side is 2-pointers only. The right side is 3-pointers only. And then this is from the offensive player's perspective on the top and the defensive player's perspective on the bottom. So this is a field goal percentage right here, and there's like a really wide range of values. It looks like maybe 0.35 to 0.65 or something like that. A lot of these are centers who only dunk essentially or take shots within 5 feet of the basket. But even if you ignore these, it's still a much wider distribution than some of these other statistics. Especially the defenders, the opponent 3-point percentage. So this distribution is super narrow. So this is basically saying there's almost no difference in players' abilities to affect their opponent's 3-point percentage. And so this is kind of known by basketball analysts by looking at data in other ways. This kind of just confirms sort of the same result, just in a different way using a different model. And so there are a bunch of other matchup adjusted stats, and essentially for all of the standard box score stats, we tried an adjusted version of all of them, and we ended up keeping most of them because they sort of improved the model essentially. So field goal percentage and 3-point percentage on contested shots. these did not make the model 3-point percentage on contested shots because they don't happen very often, and there was not enough information there for it to add any sort of value to the model. But then the rate at which they attempt field goals, 2-point field goals and 3-point field goals, assists, blocks, steals, turnovers, fouls, all of these have matchup adjusted versions that are being used in RPM, in Real Plusminus. A couple of the standard box stats remain, just points, offensive rebounds, and turnovers in the defensive model. Just another, the third bullet point that we had, the third main difference in the new Real Plusminus is we use the Bayesian regression model. And so that gives us full distributions for offense and defense. And so this is LeBron. And so he's our best estimate is around, he's worth +6 points per 100 possessions. But there's kind of a range of values here. So it's, roughly 4 to 8 or something like that is what we would estimate he was worth. This was the 1920 season, only before the bubble started. So before the 4-week hiatus or 4-month hiatus because of COVID. And then the other thing I'll point out is typically with all metrics, even if we're adding all of this, all these fancy stats from player tracking data, it's still typically harder to evaluate defense. And so we can kind of see here, it's sort of reflected in how wide this distribution is. There's more uncertainty in defense than offense. This distribution is much wider than this one. So the range of likely values of his quote unquote true ability or true value to his team during the 1920 season. It's a much wider range of likely values. And then the fourth bullet point that we talked about is we now go back to the 96-97 season. So we can make comparisons across eras, although we want to do this with a grain of salt because, first of all, the game changes over the course of time. But also we only have tracking data for 13 to 14 through present, and so we actually we use two different models for those time periods. So, but that won't stop us from making comparisons like comparing LeBron, Kobe, and Jordan. And so we've lined them up by age here. Age is on the x-axis, and then their RPM is along the vertical axis. And so, so it'll be interesting to kind of look at how LeBron compares to Jordan later in their careers. Unfortunately, we don't have any of the prime Jordan years, but maybe Jordan's prime, maybe he would have a higher peak than LeBron. It seems like LeBron's peak is going to last for longer. So this is the 1920 season. For this season, he's around like 8 or 9 or something like that. So he's he's up here still this season, and so it seems like he's gonna maybe have a longer sustained peak maybe than Jordan did, but time will tell. We shall see. So that's sort of an overview of RPM. And RPM was used on its own, but I also thought I'd talk about the Basketball Power Index, the NBA Basketball Power Index. So this is also something that the team redesigned while I was there, or at least 90% of it while I was there. It's related to RPM because basically one of the main changes is so BPI has existed. So NBA BPI, there's also a college basketball BPI. Both of these have existed for several years, but in the past, NBA BPI was team-based, so it did not use information about specific players. And one of the big changes with the redesigned version is it is player-based. So it responds quickly when there's a trade or when there's a free agent signing or there's an injury to a player. BPI will move immediately, essentially, the next time it's run. when any of those things happen. So it turns out that it's important all the time. It's even more important over the past year because all of a sudden there could be 4 players on a team who were exposed to someone who tested positive for COVID, and all 4 of these players have to sit out a few games and quarantine because of safety protocols and so forth. And so this can have a huge impact on game predictions and so forth. And that is, so that's one reason that BPI, I should mention what BPI is actually. It's Basketball Power Index, which I said, but this is a team rating. And it's very similar to RPM in that it is a team rating in terms of points per 100 possessions relative to an average team. So +5 would mean roughly +5 points per game against if they were playing an average team, they would outscore them by approximately 5 points. So this is a team rating metric that evaluates how good we think a team will be going forward. And so this is used for game predictions, as we'll talk about in a second. So knowing that someone is missing, if 4 players are missing from a game, that's important information to have if you're going to come up with a good game prediction. And so the new redesigned BPI immediately reacts to these player injuries and trades and so forth. Another big difference is it now uses player tracking data, basically because RPM uses player tracking data, so therefore BPI is using player tracking data. And then we also redesigned BPI so that we get full distributions for every metric that we get. So same kind of thing as RPM. Instead of just getting, for example, +5 for a team, we'll get the range of likely values is like 4 to 6 or something like that. And we'll talk more about that in a few slides, but this basically enables you to answer more questions, and specifically it enables you to create betting related metrics fairly easily. And so this is sort of just a high level overview of how BPI is created and how it's used. So it starts off with RPM. So that's the first thing you do. We just talked about that. Then you come up with like a predictive RPM, which is like a multi-year version. So it uses multiple seasons of RPM, and it also uses player ages and sort of like average age curves of players to come up with what do we think this player is going to do going forward, essentially. We also had created a model for predicting return dates for injured players. We'll talk about each of these a little bit more in a second. We developed a model for predicting minutes per game for every player. And that's based on, first of all, whether or not we think he's going to play. Also, who else is on the team? How good are they? How many minutes do they typically have in a game? And also, are they expected to play? Are they injured? And there's a different minutes projection for regular season. There's a model for regular season, and then there's a model for the playoffs, because typically stars play more often in the playoffs. And then BPI, once you do all of that stuff, BPI is, at its core, it's basically a weighted average of the predictive RPM. So it's like it's an average of RPM, but it's weighted by the projected minutes. So you're basically just adding up all of the player predictive RPMs, but you're weighting them by how many minutes they're going to play per game. And then the BPI is used for game predictions, predicting, so-and-so has a 60% chance of winning this game. So BPI is used for that, along with schedule information like how many days rest each team has and stuff like that. And then the game predictions are used for season projections. So to simulate a whole season and say we expect this team to win 50 games or something like that. So just a little bit more about each of these. So this is in the red here is LeBron's predictive RPM, which we saw a couple slides ago. The blue, is his RPM, and the blue is its predictive RPM. So this is just showing that this is a little bit smoother. It's using multiple seasons of data, so it's not going to overreact to one particular year. And it's also sort of using age curves. So I should have showed. Well, I don't have actually the information because I'm not at ESPN anymore. But ideally, I would be able to show what is this predicted RPM going forward, like in a future season, like 2021 or 21-22 season, and most likely it would. Since he's in his mid-30s, most likely the predictive RPM would estimate that he's going to go down a little bit. So this looks like he's about 7 + 7 for the 1920 season. It'd probably predict for the 2020-2021 season that he'd go down to 6.6 or something like that. In his case, that might be actually not correct because he doesn't seem to be aging a whole lot, or his play does not seem to be falling off any really as he goes through his mid-30s. But for the typical player, it will be an accurate, using that kind of age curve will be useful for a player who is in his mid-30s. So here's an example of estimating return dates. So I should actually mention that this is not actually the ESPN model. So like I said, I don't have access to all that stuff anymore. So what I did, this is for LeBron. So I wanted to come up with a current example. This is for LeBron. He's out. The latest estimate that I saw is that he's out until May 7th. And so what I did, for the statisticians out there, what I did is basically this is a negative binomial distribution with a mean of like 12 days. I think that's May 7th is about 12 days from now, and a standard deviation of like 6. But basically it gives this bell-shaped curve. And basically it's saying, okay, his estimated return date is May 7th, but that doesn't mean he's definitely returning that day. There's some sort of distribution of possible dates when he's going to return. And here are the likely dates, and here is how likely they are to be his actual return date. And so I just kind of made this up and made up a bell-shaped curve looking thing here. But the actual model at ESPN is built using historical injury data with expected return date, and then also what was the actual return date. So that's what's used in the ESPN model. This I kind of just made up, but it should be like a reasonable facsimile of what's going on internally at ESPN. And so BPI, so I got this from the BPI website on ESPN on Friday. And basically what this is showing is there's a BPI on the website, and there's also a playoff BPI. And so the BPI, what that is like I said, it's kind of the weighted average of the players' predictive RPM and weighted by projected minutes. And so the BPI does take into account if there's injuries. If there's injured players, they won't show up in the current BPI. So for example, for Brooklyn and Lakers, they're at I don't know, +3 or so. They're still top 10 teams in the league as of Friday. Their current roster is still a top 10 team in the league. But since they have some average injured players, they weren't at full strength, and so they BPI doesn't consider them currently as of their roster on Friday, or really as of the roster on Thursday night, I guess, is when it would have been run. They were, not one of the top teams in the league, but they were still in the top 10 or whatever. And so that's what these the circles are. These are the current BPI. The arrows show what the playoff BPI is. And the playoff BPI basically assumes anyone who's not out for the entire season is assumed to be back. So that's one big difference. And that's one reason why Brooklyn and the Lakers jump way up. It's assuming LeBron and Anthony Davis are both back. I think Anthony Davis might have come back this weekend. And then for Brooklyn, it assumes all of their players are back. I think Durant actually came back this weekend too. So maybe I should have updated this morning. But I think you get the idea. So BPI is sort of like a current snapshot. What's the team kind of look like right now? It ignores day-to-day injuries and load management and stuff like that. But if there's like a short-term injury, it's reflected in BPI. Playoff BPI is like kind of what is this team going to be like for full strength? What are they like full strength essentially? And then playoff BPI also uses the playoff version of the predicted minutes because stars play more in the playoffs essentially. So the BPIs are used for game predictions, and for several seasons they've been used to generate probability of winning a game, expected score differential, expected total score, and so forth. But now, since we have full distributions for everything, if you have full distributions of the game score, for example, you can have also full distribution of score differential. So all the likely score differentials and how likely each of them are to occur. You can answer questions like, what's the chance that this team will cover the spread? Same thing with total score. What's the chance that this team will, what's the chance that you'll cover the over for a particular game? So this is just a sort of an example from an earlier version that we were working on. So if we pretend the line is here, which is maybe a little unrealistic because this is a plus 20 line. But this is the range of possible, this is a distribution of point differential. So range of possible values of the point differential for the game. And the line is here. You can kind of just count the chance of each of these point differentials or point differential in each of these ranges. You can count all these sort of rectangles above the line or the rectangles below the line and see, well, how likely is it that this team is going to be, is going to be below the line or above the line? So how likely is it this team is going to cover the spread? And we can say similar things for season projections. We got expected win totals. These things were being created by the old BPI, expected win totals, chance to make the playoffs, chance to win the championship. And those come from just simulating the season like 20,000 times. Because of the way that we built the model, we also have distributions of win totals. So we can say, what's the chance the team is going to cover the win total, the Vegas win total. So you can come up with sort of results like this. This was for the Celtics back, I believe it was before the bubble started. What's the chance they'll go over 42 wins or 43 wins or 44 wins and so forth. And so because we have distributions for all these things, the betting metrics are actually pretty easy to derive. And so I thought I'd finish just talking a little bit about sports analytics in the COVID era and sort of what had to go on behind the scenes at ESPN with the sports analytics team. There was a ton of changes in the past year on sports because of new rules, like Major League Baseball extra innings. Rules were different. Double headers were 7 innings, so forth. Lots of neutral site games or games with no fans or limited fans. Some conferences decided to cancel their season in college football. Some conference that decided to cancel their season then said, just kidding, we actually do want to play. There was just increased uncertainty overall in outcomes of events, especially like game outcomes, like we talked about before. 4 players could just be sidelined because of safety protocols because they were exposed to someone who had COVID or tested positive for COVID, things like that. So a lot of these things sort of affect your metrics, or there are things that you want to do with your metrics to sort of account for these changes. So game predictions, had to be changed because of neutral site games and games with no fans and things like that. In-game win probability, the win probability tickers that you might see on ESPN. Those things, when there's a rule change like the extra inning rules in baseball, or the fact that double headers are only 7 innings, that affects these in-game win probability models, or even pre-game win probability models in some cases. And so some of these had to be adapted because of these rule changes and these different things that were going on. The player and team ratings, these all had to be modified a little bit. And one of the big reasons for that is home advantage. So what happens to home advantage when you're in the NBA bubble and everyone plays in the same location? So there's different aspects to home advantage, and so there are some things that you can do about this. So some of the different aspects, travel miles. If you're the home team, if you have a 5-game homestand or something, you're not traveling at all, but the people who are visiting you have been traveling. Days rest, you might have more days rest because of that. Altitude can impact home advantage. It's harder to play at Denver and at Utah than it is to play other places because of the altitude. Having the home crowd is an advantage. There have been some studies that have shown that there's some referee bias towards the home team. And so that can be an advantage as well. There's just being at home and sleeping in your own bed, being in familiar surroundings in the arena or the stadium. That could be an advantage for the home team. And that might be a little bit harder to measure. And there could be other things, other advantages that aren't listed here that could benefit the home team. I guess like hitting last in baseball is probably an advantage. The question is, how do you estimate all of this stuff? How do you estimate the home advantage that remains in the games that happened this past year? So in games with no fans, in neutral site games, in games that were not neutral site that had no fans, and so forth. So, does the home advantage that remains, does that vary by sport? So, is having a crowd more important in football? Is that a bigger advantage in football because they can prevent the other team from calling plays as easily? Is the crowd more important in football than it is in some other sport? And so, we have plenty of data for games that are either a neutral site or have no fans or only have 12% capacity or whatever. We have tons of that data now, and so we could answer those questions. And so I partly bring that up because this is an interesting problem that I don't think has really been studied publicly. So, if there's any students out there or professors who are interested in sort of sports analytics type research problems, I think this is an interesting one that's kind of timely. And so, I think you can start to answer these now that we have this data, but what do you do when you have to make these changes to your metrics between March and July of 2020 before all of these games have happened? And so it was sort of like a non-trivial thing. We just ended up guesstimating a few things and crowdsourcing what we thought the answer should be as far as how much home advantage should still remain. That was kind of like the best option that we came up with. But that's about all that I had planned as far as the pre-prepared presentation. So thanks again to the organizers for inviting me to speak, and happy to answer any questions you might have.
Thank you, Brian, for the fantastic presentation. So I have to ask a quick question first on the real plus minus, because you mentioned ridge regression and then some Bayesian regression modeling beyond that. We have some students listening in from my linear regression class who learned about ridge regression last week.
Okay.
So I'm wondering if you can tell a little more details about what's the response variable here, what are the covariates, how does the ridge component help in that?
Yeah, sure. So the response in this case would be, it's a shame I deleted a couple slides in the interest of time that actually talks exactly about this. So, so the response in this case would be points per 100 possessions. Well, let me start with the observations would be periods of time during the game when no substitutions have been made. So the 10 players on the court are the same during this period of time. So those are the rows of the data. The columns of the data would be players, and they would indicate whether or not a player is playing during this particular period of time during the game, during this shift, let's say. And then the outcome would be points per 100 possessions that were scored during that that shift or during that segment of the game. And so there would be one of these rows that corresponds to the home team being on offense, and another row corresponding to the away team being on offense to kind of separate offense and defense. You could also do it all as one row and use point differential as the outcome, but that would give you an overall rating that would be very similar to this, but you wouldn't have the offense-defense breakdown. And so the reason ridge regression is helpful is the same reason you probably learned about in class. So if there's a lot of collinearity in the data, ridge regression can be helpful. And so in the basketball case, collinearity happens because players play together often. LeBron and Anthony Davis are often on the court at the same time. So there's collinearity. Player combinations do vary, but pairs of players, there's pairs of players that are often on the court together at the same time. And so because of this collinearity, ordinary least squares is not great, especially only with one season of data. And so ridge regression is really useful. And then the Bayesian regression is even more useful because instead of shrinking everyone to 0, which is what you do in ridge regression, you're shrinking everyone towards box plus minus. So if you're Steph Curry and you score 30 points a game the first few games of the season, your coefficient's not getting shrunk towards 0. It's getting shrunk towards something that's probably like +5 or something greater than 0.
Thank you, and thank you for mentioning collinearity. That was perfect. So a couple questions came in here. So one was about the prevalence of data science teams in sports books. And so one question was about how many sports books, to your knowledge, have gained access to the advanced stats that you referenced for line setting and risk management purposes?
I don't know of any of the sports books or line makers that are using analytics. I'm sure they are. I just don't know of any specific examples. I do know there are some. So there are some companies who sort of do these kinds of things and then sell them to people who make the lines. Sell metrics to people who are making the lines. Or there are some companies that kind of sort of just actually bet with the information that they get from analytics. But I don't know a ton about that whole side. It's sort of intriguing, but I just haven't really gotten into that side of things a whole lot.
There's another question. How do you take into account synergy between players for BPI?
Yeah, so that would mostly need to be taken into account with RPM. I think there's probably ways that you can incorporate it into BPI without incorporating it into RPM. And that is not something that we did. I mean, this is our first year redesigning it. So that's something that was just something that we assumed away for the purposes of this version of RPM. We just assumed that there were basically no interactions between players, that there's no synergy, positive or negative, between players, which is probably not true. But for simplicity's sake, that's kind of what we assumed. But what you would do in a regression model is use interaction terms or something like that for players, or you could cluster like players together and then have an interaction term. Interaction terms based on those clusters. Yeah, so I think that's the answer. Yeah.
And so we have one more question here. So if you have these predictive distributions essentially for game-specific or season-specific totals or outcomes, presumably you can go down the list of all possible bets and see how much you disagree with the market. So one question is asking, can you give an example of a time when you had a big disagreement with a Las Vegas line and who ended up being right?
That is a good question. Unfortunately, I think I don't have a good example of that because we basically, BPI was sort of finished a little bit after I left. So I wasn't at ESPN when we had a final BPI model and compared it with Vegas. I will say that during the development of BPI, we were checking what are our results saying versus what are the Vegas lines say, or what are the Vegas win totals, or the Vegas chance, the odds to win the NBA Finals and so forth. So we were using it as like a sanity check, as well as using the old BPI and Raptor, the 538 version, advanced team rating. So we use those as a sanity check. Unfortunately, I don't have any good examples of like what does the final BPI say about a team versus the Vegas line.
So we have another question about how does Real Plusminus deal with players who do not play a lot of minutes or have very sparse data?
Yeah, good question. So there's a couple things going on. So I mentioned that, and kind of glossed over some of these details also. I mentioned that, like, especially early in the year, there's a lot of shrinking going on, and instead of shrinking towards zero, like ridge regression, you're shrinking towards box score plus minus. And so very early in the season, it's shrinking a lot towards box score plus minus, which the box stat-based statistics tend to be more stable with less data or fewer games, at least into the season. And so that helps. Additionally, with the box score plus minus, we're using a regressed version of that also. So if someone happens to score 40 points a game their first two games, if we're just looking only at their box score statistics, we're going to think they're the best player of all time. But what we're doing is early in the year, that will be regressed a little bit towards some average, and so we won't regress that towards league average. We're regressing the box stats like that towards the average that a player. So say the player who scored 40 points a game in the first two games averaged 30 minutes a game in those games. So we'll regress that 40 towards whatever average is for a typical player who plays 30 minutes a game. So not everyone is getting regressed to the same thing, and they're sort of getting regressed to this line where if you play more minutes, you're regressed to a higher number. If you play less minutes, you're regressed to a lower number. So that's kind of what's going on. And so players that don't have a lot of data, if they don't have a lot of minutes played, their box stats are going to be heavily regressed to some mean, and that mean will be fairly low because they haven't played very often.
Thank you one more time, Brian, for the tremendous presentation and for answering all of the questions.
Thank you. Thank you again for having me.